The aim of this talk is to provide a concise analysis of a simple two-stage probabilistic programming model. Consider the following alternating sequence of decisions x and random observations xi, which in contrast with two-stage optimization finishes with an unknown future observation of the random variable. In such setting, it may be interesting to formulate a probabilistic constraint which requires that the random variable be dominated by decisions with a probability of at least little p. Here we shall assume that the second stage decision x2 is a function of past observations of the first random variable xi1. Such probabilistic constraints may occur as part of a probabilistic program where a certain objective function f has to be minimized. In the following, we shall assume that the second stage decision x2 is an L2 function. For a more general setting, we refer to the paper below. For the ease of presentation, assume that the bivariate random vector xi follows a Gaussian distribution. Then the probability function phi defining our probabilistic constraint is Lipschitz continuous and possesses a partial gradient with respect to the second stage policy, x2. This gradient can be given a fully explicit representation in terms of the parameters of the given Gaussian distribution. Unfortunately, the probability function will fail to be differentiable unless it is evaluated at a second stage policy which is continuous. In the latter case, the probability function has also a partial derivative with respect to the first stage decision, which can be given a fully explicit representation too. Let us consider now a probabilistic program where we want to minimize the expected costs of decisions subject to the earlier introduced probabilistic constraint. We may look at this problem in an iterated fashion, where in an outer loop we minimize over the first stage decision x1, and in an inner loop for any given first stage decision we minimize over the second stage policy x2 and the accordingly conditioned optimization problem. Exploiting the previously obtained gradient formulae, we may derive necessary optimality conditions for this problem, which lead us to the fact that the optimal second stage policy is necessarily an affine linear function whose slope is given by the ratio of covariance and first component variance of our random vector. Since affine linear functions do not belong to L2 of R unless they are identically zero, we derive that there does not exist any solution in the L2 space. We may circumvent this issue by allowing our second stage decision to be not just an L2 but an arbitrary Borel measurable function. Exploiting our earlier guess on the affine linear structure of the second stage decision and combining it with the concavity of one-dimensional Gaussian distribution functions over the positive reals, we may employ a direct argument in order to identify a global solution of our probabilistic program. It turns out that the optimal first stage decision is found as the minimum of some explicitly given smooth one-dimensional function, whereas the optimal second stage decision gets exactly the affine linear shape we have guessed before.